In 1543, Polish astronomer Nicolaus Copernicus published on the revolutions of the orbs of the world. He proposed the heliocentric model, where the Earth and planets revolved around the Sun, as opposed to the popularly accepted geocentric model, where the Sun and planets revolved around the Earth. Despite being revolutionary, Copernicus's proposal was still fundamentally different from our current model of the solar system, for his model still assumed perfectly circular orbits. The publication sparked many debates as to whether the geocentric model or the heliocentric model was true. Then, a man named Tycho Brahe rejected both, and proposed observing the sky itself instead of arguing in abstract terms. In his private observatory, Brahe recorded his observations of the sky for many years and built up immense tables of data. When Brahe passed away, his assistant Johannes Kepler studied the data and found that the orbits of the planets followed 3 laws. Kepler's first law states that each planet goes around the Sun in a curve called an ellipse, and not in a perfect circle. The ellipse is not just any old oval. Mathematically, it's the set of all points where the sum of their distances from 2 fixed points is constant. These 2 fixed points are called the foci. In our solar system, Kepler proposed that the Sun was one of the foci of the ellipse. Kepler's second law states that the planets do not go around the Sun at a constant speed. Instead, they move faster when they're nearer the Sun and slower when they're farther away. This is Mercury, whose orbit has the highest eccentricity in the solar system, meaning its orbit is the least circular out of all of the planets. Thus, if you look closely, you can see its difference in speed when it's closer to the Sun and when it's farther. And it turns out the planet's speed is such that the radius of the orbit sweeps out equal areas in equal periods of time, like shown. Finally, many years after he published the first 2 laws, Kepler published his final law. This particular law didn't focus on just one planet, but rather how one planet could relate to another. Before describing Kepler's third law, let's define some terms. The orbital period of a planet is the amount of time it takes a planet to go around its orbit once. The orbit size is the length of the greatest radius of the elliptical orbit. This is also known as the semi-major axis. What Kepler's third law states is that if you compare the orbital period and the orbit size of 2 planets, the periods are proportional to the 3/2 power of the orbit size. Or you could say that the squares of the periods of any 2 planets are proportional to the cubes of their orbit sizes. Thanks for watching this animated lecture on Kepler's 3 laws.